Okay, Assalamualaikum warahmatullahi wabarakatuh. And very good morning.
Salam, Doctor.
Okay, so I hope that everybody can hear my voice very loud. Okay, today we in the second half of lecture. Okay, previously Dr. Azmah start from the first half. So Hafizal bin Yahya, okay, in charge of the second part of this lecture. Basically, before we proceed, I would like to make a clear confirmation about the about our schedule for the lecture slot. Okay, actually, for the section 1, we have 2 slots in a week. So supposed to be in on Monday and start from 11 to 1. We have today start 9 o'clock to 11 o'clock. So supposed to be for the courses of the material science, we need to fulfill 3 hours in 1 week. So because of the mix between senior and February intake, so difficulty in the timetable. So Dr. Azmah is on Monday for the senior and on Tuesday for the February intake. Okay, so Dr. Azmah will make a lecture, same content twice. Okay, so for that way, I'm not quite comfortable because of the same section. I need to give twice the same lecture. So I would like to make it alternate. So in this week, I give a lecture to all senior and February intake. So yesterday I already give a lecture, and today because it's the first time we meet, so today I will give the lecture. For next week, there will be only 1 lecture on Monday. Okay, on Monday for the senior. So on Tuesday there is no lecture, but on Monday I will record the video and then I post the video on YouTube, so that after that I will share with you the link and you can watch the content. Okay, so next week only 1 lecture, which is on Monday. Okay, but on Tuesday there is no lecture, but the content you can be accessed by using a YouTube link. Okay, recorded. Okay, for the next 2 weeks, okay, next 2 weeks there will be a alternate, so that on Monday there is no lecture, okay, and for Tuesday there is a lecture, okay, and for the lecture I will record and I will share the video recorded for the senior or for the lecture on Monday to see to watch the recorded video. Okay, so only weeks, 1 week I will make a lecture. So I alternate. Okay, next week there is for your slot, February slot. On Tuesday there is no lecture until lecture we will continue in 2 weeks time. Okay, so from time to time I will inform to our WhatsApp group. Okay, so for this February intake, expected around 10 or something student. Okay, because due to the timetable, because of coming because of the timetable already start, so you cannot manage to join the rest of the lecture. Okay, so it seems that a little bit slow because of the once a week only one lecture, supposed to be 1 week 2 lectures, so a little bit slow. So we have left only 6 weeks. So in 6 weeks we need to cover 3 chapters, which is chapter 5, chapter 6, and chapter 7. So my planning is to divide this chapter by 2 weeks, something like that. In 2 weeks, we need to cover 1 chapter. So we have 6 weeks, we need to cover 7 chapters. 3 chapters left. Okay. So we have the main part of this 3 chapter is from the chapter number 6, is related to the analysis of materials, specific material. Okay. So any questions so far? So for the rest, I will give a lecture by using this slide, and I will record, and then I will make a video and publish, okay, to YouTube. Okay. And for the material for the PowerPoint, I also upload here on the e-learning. Okay, so please check your content, our e-learning. Okay. So for today attendance, please log in today attendance. Okay. Because this is very important to track you whether you are follow the lecture or not. Okay, because of need to fulfill this attendance. Okay. Right. Okay, let's we move to next slide. Okay, actually for our first meeting, we will cover chapter 5, which is dislocation and metal strengthening mechanism. Okay, in this chapter, I divided into 3 parts, okay, which is part A, part B, and part C. Okay, for the part A, we will cover of the material deformation. Actually, the material deformation, including dislocation, some information in this part already covered in the previous chapter, okay, including the stress strain curve, elastic and plastic deformation, and also the dislocation, including the defects of the materials, okay, related to foreign material in the metals, or we call it interstitial, and also the vacancy or something like that. Okay, so in part B, we will cover the metal strengthening. Okay, this is how we need to know, we need to understand the fundamental information for the manipulating the parameter for the application. Okay, so material that we need need to study, we need to analyze actually material we need to produce up to the specific application. So we need to understand more on the metal strengthening. Okay, and part C, we will cover the cold working and hot working. This one related to the heat treatment, the parameter that we mainly use in the metal strengthening process by using cold working and hot working. This one related to the the temperature manipulation. So in this slide, I will continue. I will start to make a lecture for the material deformation part A, and after we finish part A, we will continue part B. Okay, so the metal strengthening mechanism. So for the actually we need to understand the definition of deformation. Basically, the deformation is the word from deform, which is the change. The object will change its shape to a certain specific shape that we need, that we want. Actually, we want to make it the specific shape. We need to introduce a force. Okay, we give extra force. Whether the force will come in the different ways. Okay, by compression, by tensile, by shear. Okay, and finally we would like to have the shape that we need. Okay, for the suit for the application. So the mainly for the old days, the people use this kind of method to form object, especially for the molten metals, okay, by using a casting process, whereby the casting process, like we have the cast like a mold. So the specific mold design with a different shape, and then the molten metal will pour into the casting. Okay, and finally during the solidification, the metal start to reduce its temperature, and finally at the room temperature, and we can get the final product suitable for our application. So in this case, there is a gold metal gold casting, whereby the casting the mold is at the shape of rectangular, and finally the box of the metal gold ingot or casting, or the final product will take place. Okay. So other operation for the deformation may be related to the sophisticated or the machine related to the process, such as we have the rolling to deform a metal. We have the sheet metal, okay, and then we start to use a rolling machine to produce a final product like a cylinder sheet, something like that. And other technique, we use forging by introducing a force, okay, to produce a design specific shape that we want, and also the extrusion, whereby if we want to deform like a rod, the initial shape like a rod, cylinder rod, and finally we want to obtain like a rectangular rod shape, something like this. So the original is some kind of rod in cylinder, and the final product is supposed to be different shape, like a rectangular like a wrought iron or something like that, the twist process. Okay, and also the steaming process. Okay, and the final product will produce like a rod kind of cylinder, and different and many more techniques that we can use by using a machine, and final product, okay, can be used for the desired application. Okay, basically material may experience two kinds of deformation. Okay, the first deformation is supposed to be elastic deformation, and the second one is a plastic deformation. Okay, the deformation is we have the term of elastic and plastic deformation in our previous lecture, whereby we look at the process of deformation by introducing a tensile test. Okay, when we introduce a tensile test, the metals start to deform, and you can see the data can be gathered by producing a curve of stress strain curve. Okay, from there we can see the curve can be divided into several parts, which is elastic area, whereby we call it elastic deformation area. And at a certain limit, the elastic will transform to the plastic deformation. The plastic deformation area is quite a big area. And finally, if we increase the force at a certain level, the metal will break. Okay, at that point we call it fracture. Okay, so there is a certain boundaries that have the limit of elastic, we have the limit of plastic, and finally rupture. Okay, so for the deformation, mainly we will talk about the plastic deformation, but elastic deformation is basically at a certain range. When we introduce the force and the metal will deform a little bit, okay, or we introduce a tensile, the metal, let's say we have the rod cylinder metal, they will start to elongate at a certain length, and once we remove the force, it will spring back to the original initial position. Okay, so that one we call it elastic deformation. Okay, the elastic deformation is basically in the graph is a linear straight line. Okay, but at a certain limit, it will break to the plastic deformation, whereby the plastic deformation is the area where the deformation is permanent. Okay, maybe you can imagine the process of when we use a spring, okay, spring, and then we pull the spring, okay, or we give extra force at a certain level. When we remove the force, the spring will back to the initial position, and when we introduce a higher force, okay, so the spring will expand, and when we remove it, it will not spring back to the original position. That is the analogy of the metal. Also the same happen to the metal. Okay, the analogy of spring can be explained same as the mechanism in the metal. Okay, so basically in this chapter we will mainly deal in the region of plastic deformation. So in plastic deformation, the area we can manipulate, okay, to the final thing for the metals, whether in the curve, we need to study the curve. We need to produce the metal as strong as it can. Okay, so the metal is supposed to be strong so that it will suit for the certain application. So we need to understand the basic information of the metals in the plastic region, so that we can manipulate it to suit it to certain application. Okay. So in the plastic, elastic and plastic deformation, just now I already mentioned to you. So for the stress strain curve is basically something like this. We have several areas. We have the elastic deformation area in this one, but mainly in this chapter we will deal with this area. Okay, elastic deformation. Sorry, this one is plastic deformation, not elastic deformation. Okay, this area we need to manipulate it. Okay, because the curve, you can see we can manipulate the curve by make it higher curve. Okay, once the curve higher, the stress is quite high, so the yield strength, the strength is very good. Okay, if compared to the initial, okay, before we manipulate. Okay. So actually the characteristic of elastic deformation according to the stress strain curve, we can gather the information such as that one is a non-permanent deformation, okay, which appeared and disappeared with the application of removal the stress. Okay, that means we can focus on the elastic area whereby the graph is in linear at with a certain slope or gradient. So once we start to apply the force, we will start to elongate at a certain length, and once we remove, it will spin back to the original position. So next is the over short range of stress strain curve. Okay, this one is basically the explanation is based on the stress strain curve. When the stress is applied, displacement of atom from original position. Okay, so the elongation of metal at a certain distance. Okay, so when we remove if we talk about the mechanism in terms of atom, the position of atoms. Okay, once we apply the force, the atom at the initial position is a vibration between atoms, okay, with the bonding, okay, between neighboring atoms. Once we introduce the force, the atom will start to make a distance between neighboring atoms. So we will not break to the bonding, so that when we will only stretch a little bit when we remove the force, and it will produce the atom will spring back to its original position. Okay. So for the plastic deformation, the characteristic is based on the plastic deformation area in the stress strain curve. Is basically the permanent deformation. Okay, where it sits over the boundary of the elastic deformation, it will go for the permanent deformation. Even if we remove the force, it will stay at the final shape of the shape after we apply the force. Okay. So over the range of stress strain curve, so if you compare to the elastic deformation area, the plastic deformation area is more bigger area. So it's very important to understand this area because we can manipulate to increase the strength or we make a higher value of curve in order to get the more valuable of the metals for the sake of the application. Okay, when stress is applied, correspond to movement of many atoms. Okay, and if we want to talk about the mechanism of the atom, okay, the atom we will sleep basically is not stretched anymore, and for the plastic deformation, the atom will slip. Okay. After this, we will see the several type of slip, plastic deformation for the atom. Okay. Okay. So this is the illustration of the elastic deformation. Okay. Let's consider the metal bar here, and before we introduce the force, okay, in this condition, and then when we want to look at the mechanism of the what is happening to the atoms, arrangement of atom in this area, and if we want to look at the stress strain curve or what will happen to the elastic deformation. Okay. In this case, we will apply for the tensile test. Okay, the tension we give to the metal bar here, and this is the original position. Okay, once we apply the small load, okay, the atomic arrangement at the stacking level will start to stretch at a certain distance, and the elongation of the metal bar here at a certain distance here, we can see the elastic formation takes place around here. And for the stress strain curve is basically in the straight line. Okay. So once we remove the load, the atom will spring back to its original position, and we can see there is the curve will back to the original or the origin position. Okay. If we want to compare to the plastic deformation, okay, the plastic deformation will, if we apply the tension, the atomic arrangement in this stacking layer of the atomic at a certain position will start to slide. Okay. In this case, we can see the original position here. During the process of applying the force, we have the slight distance produced here, and you can see arrangement of atoms is stressed, and some of the atom is slip at a certain plane. Okay, we call it plane shear. Okay, or planar shear. In this case, we can see the slot or the small portion of the atomic arrangement is slip at a certain direction. Okay. So once we remove the load, the atom is plastic deformation will produce, and you can see the original, the initial atomic position will now change to the different shape. Okay, in this case, there is a shear of the plane taking place. Okay. So after this, we will see the clear picture, the atomic arrangement, the drawing, the illustration, and the real image of the metal atomic displacement. Okay, for the plastic deformation. Okay, basically the plastic deformation can be occurred under the different applied force. Okay, the first one is a tensile. The tensile whereby we introduce the force is something like this. Okay, and for the compressive, we can apply something like this. Okay, and also we have shear is something like this. Okay, so the plastic deformation, there are two basic model. Okay, when we talk about the plastic deformation, because if we look in the macroscopic, the atomic arrangement, we can see the differentiate between the two types of the model. The first one, they have the slick deformation model, and the second one is a twinning deformation type. Okay. So for the slip deformation is basically related to the sliding atom planes. Okay. Just now we see the slip of atom at a certain direction. So at the plane, the plane of atom, arrangement of atom in that plane start to slide, okay, at a certain direction. Okay, and the crystal orientation, meaning the direction of the atomic arrangement will be slip if compared to the above and below planes. Okay, and we can see the atomic movement at the plane will start to move at a certain distance. Okay, this one is required a lower stress for the atomic movement. Okay, so if compared to the twin deformation, okay, there is a quite higher stress compared to the plastic slip deformation. They occur in widely spaced plane, and if you can see from the this diagram, you can see there is a slip taking place in this part, and also this part there is a slip in this direction. Okay, so even though we introduce direction of force that like a compressive tension force, okay, but the slip is happen to the right or to the left, okay, according to the plane. Okay, it seems like we introduce shear stress, okay, on this, okay, on this area, this metal spar. Okay, deformation by slip, basically adjacent plane of the crystal. Shear stress move upper planes, atom to the right. Okay, this the upper area, basically like to the right, but the lower to the left. Okay, movement occur when shear stress exceed critical value. So at a certain position, the value of the force we will give exceed a critical value and start to slip. Okay, if not, it will stay at its position. Okay, so if we look at the two-dimensional diagram, so we can see from the atomic arrangement in this area. So once we apply the shear stress, the atomic will start to move to the right, and finally it's something like this. Okay, so we can see there is a boundary, the area, the certain boundary that the most of the atom in the upper region slip to the right. Okay, the red in color line is, we call it the slip plane. Okay, and it's also happened to this diagram, the same thing, but we can see there is the shear stress applied here. You can see the movement of atom in the crystal lattice, and finally the final position of atom, whereby is produced here. This area we call it a slip step. Okay, and if we want to look at the three-dimensional picture, okay, the same thing happen, but in three-dimensional 3D, we like to look at the X, Y, and Z direction of the plane. Okay, in the yellow color, this is the plane. We call it the slip plane, whereby the upper or bottom of the this position of atom is twist to the left and to the right. Okay, So for the in the real image of the process of slip in plastic deformation, as you can see, this is image is taken by using a electron microscope. It's not use the optical microscope. We cannot see the like a microscope, ordinary microscope that we cannot use to see this kind of thing. But to look at these things, we need to use the electron microscope. Okay, in electron microscope, we can see there is the slip of the orientation of the atomic slip taking place all over the area. Okay, as we can see from the 2D area, we can see like something like the small chunk of this part of the atom slip to this direction. Okay. So for the in the actual the reality is the slip and it's not happen alone, but there is a mix with other twin in plastic deformation also. Okay. For the twinning in plastic deformation is basically the same as slip, but in twinning there is we call it like a mirror image of the atomic position is something like this. Okay, so if we look at this initial position, the atom is arranged something like this, and this is in the yellow box color. Is basically the deformation takes place. We call it twinning. The twinning like the position of atomic arrangement is something like the initial. We have the rectangular position, but this is the twin of this initial position. Okay, so the same thing like we lipat kertas. So we have the A4 kertas, and then we divide into two. Okay, like the mirror image of the original position here. Okay, so in this part, the model there is we call it twinning deformation. Okay, so the atomic movement over a fraction of atom, but in this case the fraction of atom is quite bigger. Okay, but the like a symmetrical of the initial position of atom. This one required higher stress in order to make a deform is something like this. If compared to the slip, you need less stress. Occur on every atomic planes, okay, involved in twinning region. Okay, if you want to look at another deformation takes place, let's consider the image here. Okay, please look at the position of atom in this line. Okay, we have the red color. Once the twinning takes place or the deformation takes place, the atom in this line will start to translocation in this position. Okay, all those atoms will move in this area. Okay, and produce a kind of a deform of the atomic bonding here. Okay, so in this case we can see the chunk of this area. Okay, the line here, and also this line here, we call it the twin line. Okay, so this area we call it the twin region. Okay, because of the call it twin region because of the mirror image of this area, like we hold the A4 papers. Okay. So this is the line. We call it the twin plane, or we call it mirror plane. Okay, so the direction of the atom in this direction. Okay, downward direction. So for the actually metal usually deform by twinning when it's unable to sleep. Okay, so there is in real world there is two model will take place in one area. Okay, so we can see a sleep and also we can see a twin deformation in one area. Okay, so twinning produced by the shear stress, okay, known as the mechanical twins, occur in BCC and SCP metals at low temperature. Okay, and also for the uh, annealing process, the annealing is basically we introduce temperature at a certain degree. So this one also occur in a certain FCC metal, okay, especially for the copper and gold. So this is the microscopic image of the real condition of the happen of the deformation in slip and twin. As you can see, there is a twin. Twin is basically quite a bigger area deform, and also slip. You can see like something like this. Okay. So in real condition, we can see two deformations taking place at the same place. Okay. So, and if you can see in this diagram, there is a grain boundary. Okay, the orientation of the atomic arrangement in the grain boundary, we can see quite a different orientation. Okay, in this case, we can see there is the twinning taking place at this direction, and also the twinning happen at this direction. So at this one, the grain boundary in this area, also in this direction. So actually, the grain boundary play important role to stop the twinning's migration. Okay, as you can see here, there is a grain boundary. The boundary stop the twinning happen. So because of the deformation, we have the slip and twinning. So if we have a bigger grain boundary, the migration of the movement of twinning deformation will keep longer. Okay, so it will weaken the metal. Okay. The final product, we would like to have the metal that strong, that suit to the application. So in order to get the metal strong, so we need to manipulate also the grain boundary to make it smaller. So once we try to make it smaller, the distance or the length of the slip or twin become shorter. So it will make a stronger metal. Okay, if the deformation is long, so it will reduce the strength of the metal. So for the then we will deal with the dislocation. Okay, but the term dislocation is basically very important to understand because of the dislocation is once you heard this term is in the previous chapter, we have the dislocation whereby in the defects, okay, we have case dislocation and also we have the screw dislocation. So in this dislocation is basic in plastic deformation correspond to the motion of dislocation. Okay, so we need to understand the dislocation motion in order to play around with the condition to produce a better metal, okay, in terms of strengthening the metal. So the plastic deformation occur when large number of dislocation move. Okay, so when we look at the stress strain curve Okay, and then we go for look at the plastic deformation area. As you can see, there is a very large area if compared to the elastic. So this large area is basically due to the dislocation move. Okay, the motion of dislocation. So the longer of the movement of dislocation can move quite far, the plastic deformation will affect. Okay, so we need to understand the fundamental basic information from the microscopic view of deformation in terms of atomic movement. Okay. Can anybody hear me? Right. Okay. So, other word, the movement of dislocation in the material is allowed to the deformation. Okay. Once we have the dislocation move, so the deformation will take place. Okay. So this one associated with the dislocation and deformation. Okay. So this more dislocation, the movement dislocation can happen, the deformation will taking place. Okay. So the dislocation is a linear disturbance. Okay, that one is in the atomic arrangement, as you can see from the dislocation in the plastic. In the sleeve and twin dislocation. As you can see, the atom move in the straight line in the planar plane. Also occur during solidification. Okay, this one we already know. During the solidification, the dislocation or defect which takes place. The motion is called slip. We already explained previously. Movement can be stopped by boundaries. Okay, previously I also explained the grain boundaries, the purpose of the small grain, the biggest grains. Okay, so the grain have its different orientation between the neighboring grain, so it also has the boundaries. The boundaries will act as the stopping to block the movement of dislocation. Okay, especially from the slip and twin. Okay, this one act as a barrier to protect the dislocation move longer and longer. And finally, the metal will weaken the metal. Okay, and have tendency to multiply during deformation. Okay, for the dislocation, we have two types. The first one is edge dislocation, and the second one is the screw dislocation. You already covered in the previous chapter. But okay, for the part B, we will look at the strengthening of metal. Okay, or metal strengthening. So in this part, it's very important for you to understand the manipulating of the by using a parameter that we can manipulate to strengthen the metal. Okay, especially in the plastic deformation region. Okay, all this information is related to the plastic deformation. For the elastic deformation, we not talk about the elastic deformation, but in plastic deformation, that's many things can be manipulated, okay, including the strengthening of metal. Okay. So for the final product in the metal production, okay, related to metals, okay, because of the product from the metal is widely used in many different applications. So we need to understand the application, and also we need, before we want to apply for the application, we need to tailor it to the its mechanical properties. Okay, so we need to look at the strength, to look at the ductility, to look at the toughness or something like that. Okay, the previous lecture you already learned about the mechanical properties. So we need to tailor to its mechanical properties. Okay, in terms of the make it strengthen, how we want to make it strengthen. Okay, what is the mechanism we want to use? Okay, how the strategy that we would like to introduce. Okay, in order to produce a very high strength of metal or something like that. Okay, so we need to understand the basic knowledge of the, especially for the curve, okay, the stress strain curve. So in order to make it stronger, we need to manipulate the information, something like that. Okay. So in this case, we need to have a basic concept first. Okay. In the basic concept, basically we talk about the dislocation movement. Previous lecture, okay, previous slide. In part A, I already mentioned about the dislocation movement or the dislocation motion associated with the deformation. Okay, once the dislocation movement can be easily moved at a certain length, okay, the deformation will also taking a place, okay, and it will soften the metal, or it will make a less stronger the metal. Okay, so once we know the dislocation movement, and the next step, we would like to have the strategy to strengthen, whereby we need to block the dislocation movement, okay, or restrict or hinder the dislocation movement. Okay, so in order to restrict the dislocation movement, we need several tactics to deal with this. Okay, we have 4 tactics or 4 mechanisms that we can use. The first one is grain size reduction. Previously, I already mentioned about the grain boundary size. The smaller size is better to reduce the movement of dislocation, especially for the slip and twinning dislocation. And also we have the solid solution alloying. This one related to the how we manipulate by using a foreign material. Okay, we put foreign material inside in order to strengthen the metal. Okay, the third one is strain hardening, and the fourth one is the precipitation. Okay, hardening. Okay, after this we will cover it all, but in part B we only covered at number 2, solid solution alloying, and part C will cover the rest. Okay, so in this part we'll cover until number 2. For the basic concept for the dislocation movement, is very important to understand because of the dislocation motion or movement associated with the deformation, but the deformation associated with the mechanical behavior. Okay, especially for the mechanical properties lah. Okay, we have the strength, stress, we have toughness, we have the ductility, and many more. Okay, to discuss. And for the dislocation motion is ability of the metal to be deformed. Okay, depend on ability of dislocation to move. Okay, so this one very effect of this dislocation. Restriction dislocation motion make the material stronger. Okay, so how we want to restrict the dislocation motion? We need to block the dislocation by using 4 tactics after this. Okay, the more unconstrained the dislocation motion, the easier the metal may deform. Okay, the same things in the word. Okay, how to block? Okay, the strategy is to block the dislocation motion by reducing the mobility of dislocation. Okay, one we make a block like a boundaries. Okay, when we set the boundary, the dislocation motion will stop or will reduce the mobility. Okay, it still will move, but at a certain distance. Okay, not longer distance. Deformation become difficult. Okay. Okay, once it become difficult, and finally it will stop there. Okay, greater mechanical force required for deformation. Okay, so once the deformation or dislocation motion stop, okay, it will occur, but it will need a greater force. Okay, for the deformation. Okay, then a mechanical strength is enhanced. Okay, okay, the final objective. Okay, and restrict or hinder dislocation motion will make a material harder and stronger. Okay, that is the things. So we will go one by one. The first one is this one, grain size reduction, solid solution hardening, strain hardening, and precipitation hardening. Okay. So once if you we have a question required you to explain about the what is the mechanism or tactics to hinder or to block the process of the dislocation movement, you will be able to highlight about these things, okay, and explain it, okay, to make it clear, okay, one by one, okay. So we will go for the grain size. So we must be understand about the grain size produced, especially during the solidification process or crystallization process, whereby from at a certain temperature it will reduce at room temperature the atomic arrangement taking place, and it will produce a grain size, okay, grain boundary at the neighboring, and many grain boundaries will produce at the different orientation of atomic arrangement. Okay, as you can see, we have grain A, red color, we have grain B, green color. So in grain A, we have the orientation or the direction of atomic arrangement is in this line. Okay, but in grain B in this line. Okay, slightly different in angle between two. Okay, so during the process of the dislocation, okay, the deformation taking place, we look at the dislocation movement, and if you can see from the slip plane here, this dislocation taking place at this area, whereby we have the atomic arrangement move to this side, okay, and the line of the dislocation hit the boundary here. Okay, so if we the boundary acts as a blockage of the dislocation movement. Okay, in this case we can see the mechanism of dislocation movement, whereby it's blocked by the grain boundary. Okay. Okay, during the plastic deformation, dislocation movement will try to go through common boundaries. It will try to cross these boundaries, but it will block by the the boundaries here. Okay, so if we can see the orientation here, okay, the direction of red atom here, this direction. If you can see, the green direction is here, slightly at a certain angle. Okay, if the higher angle, okay, let's if we have the direction of green is something like this, if compared to the red, it will produce a higher angle. If the higher angle is, it will make a stronger block to the dislocation movement. Okay, so after this we will see the difference between the higher angle and low angle to the effect to the dislocation movement. So of course the grain boundary act as a barrier to the dislocation motion. Okay. Okay, and finally it will become difficult to the dislocation motion to go to penetrate, and it will stop there, and it will make us stronger metal. Okay, grain size can be controlled. Okay, whether we need to control the bigger size or smaller size can be controlled by using a rate of solidification. The process of solidification, we can make it faster or slower by introducing a cooling process. Okay, so some of the solidification we let it solidify at room temperature, slowly solidification, or we make it faster solidification by introducing into the cooling machine. Okay, we put in the cooling machine, it will very fast cooling rate. Okay, so it will affect the grain size also. Okay, and also the plastic deformation also affect the grain size. Okay, and of course for the treatment of heat. Okay, at a certain temperature, at a certain melting point. Okay, after this we will see more on the heat treatment, especially for the annealing process. Okay, related to the heat. Okay, fine grain material has a greater total grain boundary surface area. So if we have a very small grain size, that means we have a very short distance of dislocation movement. Okay, and finally it will block by the boundaries. If we have a bigger size, the dislocation motion movement will have a very long distance. Okay, so if compared to the smaller and bigger size, the smaller can have a greater surface area that will block the dislocation motion. Okay, so and finally we will produce a very strong metal. Okay, can prevent more dislocation motion, and finally we can have a other stronger material. Okay. So in this case, if we look at the stress strain curve for the stronger or harder material, the curve can be produced higher curve at a certain yield strength. Okay, so it will increase the yield strength. So the relation between the grain size, okay, produced and the yield strength can be achieved by using this equation. We call it Hall patch equation, whereby the sigma y and sigma 0 are related, whereby the sigma y is yield strength. The yield strength is equivalent to sigma 0 plus KYD power by negative half. Okay, and whereby the D is average grain size diameter. Okay, the size is showing the value of the yield strength. Okay, so and then for the grain size reduction, basically the process of the producing of the smaller or higher bigger grain size. Okay, and if you look at the grain size in terms of the atomic arrangement, we can see we can associate with the barrier, okay, the grains size barrier, okay, or boundaries. Okay, in this case, we can have several diagram related to the grain size, grain boundary. Okay, in this case, because of the grain boundaries, it actually act as the blockage of the dislocation motion. We will have a kind of grain boundaries. Okay, the first one we have the twin boundaries. As you can see in this case, we have the mirror image of this atomic arrangement with the grain 1 and grain 2. At the interface is a boundaries whereby we call it a grain boundaries. In this case, which is the mirror image of the orientation, the atomic arrangement, they call it the twin boundaries or twin plane. Okay, boundary have two different phases. Okay, can prevent the dislocation motion. Okay, here is the, if we look at the grain size difference between neighboring grain size and also the orientation. As you can see, there is a grain boundary here, whereby the orientation of this grain is something like this, the direction. Or if you want to look at this direction is okay, but if compared to this grain boundary green area, this direction is here if compared to this direction. Okay, so if you can see here, if you look at this line, you can see a very high angle of the green boundary if compared to the neighboring these two. Okay, if compared to this, we have a slightly small value of the angle. Okay, what happened between two higher and lower angle? So for the higher angle, it will produce a very difficult blockage for the dislocation to move. Okay, through. Okay, for the small angle is produce blockage slightly small, resistant to the dislocation movement. Okay. And if we have a very high force, it will this blockage it will start to break. Okay, and it's not the blockage level is not good as this area. Okay, for the high angle. And finally, we will cover the solid solution. Okay, actually the solid solution whereby we introduce foreign material. Okay, or other term they call it impurities. Okay, so if compare why we need to introduce impurities or foreign material in the molten metals or the pure metals. So we need to understand the pure metal behavior. Okay, for the pure metal behavior is basically soft and weak. Okay, as you can see, the stress strain curve is something like this. Okay, let's say we have the pure metal of gold. Okay, okay, the very good analogy. You can see the pure metal of gold. Okay, the pure metal of gold we call it 100% gold. Okay, so the gold is very soft and weak. Okay, okay, the gold is very precious. Okay, for the in term of to wear. Okay, nak buat cincin, nak buat gelang apa semua tu, we need to put foreign material, okay, to make it harder. Okay, but if we pakai cincin with the 100% gold, it's very soft. Okay, it cannot stay longer the shape. Okay, once we hit by force, it will start to deform. So in order to wear a cincin or wear a gelang, so we need to make it harder to make it tap at its own shape. Okay, so we need to introduce the impurities. Okay, or we call it a foreign element inside. So once we introduce the foreign element, whether more than two foreign element, so the metal, they call it alloy. Okay, so we have different type of alloy. If we have aluminium, we put small portion percentage of foreign material, we call it aluminium alloy. Okay, if we have copper, we put a small portion of foreign material, call it copper alloy. Okay, so once we introduce the foreign material, the graph stress strain will produce a higher position, something like this. So, and when we look at the yield strength is much better at a higher position, so the strength is more better than the original pure metal. Okay, that's why in the solid solution hardening, okay, they introduce foreign material or foreign element to make it stronger. Okay, so I already explained the alloy. Please let's look at the definition of alloy. Is a combination of metal or metal combined with one or more other elements, or we call it impurities. Okay, when alloy cool or solidified, it will change its mechanical properties. Okay, the mechanical properties, if compared to the pure metal, slightly better than the alloy. Okay, so for example, if we have the combination of metallic element gold and copper, it will produce a red gold. Okay, if we have silver combined with copper, we have a sterling silver. Okay, so they're not calling a silver alloy or something like that. There is a new name after the combination. Okay, so they call it sterling silver. And then if we have aluminum copper, they call it aluminum alloy. Okay, so various percentage of copper they will put depend on its application. Okay, so the strength also produce a different strength. You introduce a different percentage of copper. Iron and combination with carbon small amount will produce steel. Okay, they're not calling iron alloy, they call it another name, they call it steel. Okay, okay, the combination of aluminum with copper, magnesium and other material, manganese, silicon, tin, zinc, will produce aluminum alloy. Okay, so many things can be produced by combining a different percentage of impurities. Okay, so for the pure metal is basically very soft. Once we introduce impurities, it become more stronger and harder. Okay. Okay, for the steel, okay, basically when we have iron and we introduce carbon at a small portion, it will produce a steel. Steel is basically mainly used in the application of nowadays we have building of bridge, building of building. Okay, so we use a lot of steel, okay, for the construction. Okay, so if we graph of stress strain curve, okay, if compared to the pure metals, okay, the yield strength gain at a certain increase. Okay, so for the purpose of the introducing impurities will help for the yield strength to increase at a certain level, and finally it will produce a metal more harder than the pure metal. So what is the purpose of the putting the impurities? Okay, the impurities is basically act as a diffuse and segregate around dislocation core. Okay, because of the dislocation is basically still happen in the grain boundaries. Okay, or in the atomic arrangement. So the impurities will help to diffuse and segregate around the dislocation core, and the atom of the impurities atom will penetrate in that area of the bonding between atoms. Okay, so we have two type of impurities size. Once the smaller if compared to the pure metal, okay, and once we have the bigger size if compared to the pure metal. Okay, so it will produce a different stress between the bonding between atoms. Okay, so for the solid solution hardening, basically we have the impurities atom. Okay, from there the atomic arrangement it will macam kacau lah. It will disturb or segregate around the dislocation, and it will produce a lattice strain. Okay, lattice strain. It will penetrate at the bonding between atom. It will start to produce a strain. Okay, once it produces the strain, it will block the dislocation motion. So how it block the dislocation motion? We will see these two type of size of the impurities. Okay, the smaller impurities if compared to the bigger atom of the pure metal, it will produce kind of a tension. Okay, whereby the smaller, okay, the tension around the smaller size of the impurities. Basically, it will happen when we introduce the smaller impurities atom. The dislocation is basically happen at the upper at the plane area. Okay, this upper area of the dislocation line here. Okay, if compared to the bigger size, okay, if we use a bigger size, the dislocation is basically happen at the lower dislocation line here, whereby when we introduce the bigger size, the compression taking place. Okay, like this. Okay, and then tend to concentrate at opposite to dislocation and below slip line. Okay, so from there we block the dislocation motion, and it will start to strengthen the metal. Okay, so we at the end of our lecture,